Okay. Hello everyone, this is Muhan Zhang. This presentation introduces a novel inductive matrix completion method based on graph neural networks. Recommender systems is an important relational learning problem and has great economic value in the real world. A classic formulation is matrix completion. Taking movie recommendation as an example, in this matrix, each row represents a user and each column represents a movie. Each user gives ratings to the movies she watched. Our task is to complete the partial rating matrix so that we can recommend movies to users according to the completed matrix. The most popular matrix completion methods are based on matrix factorization. That is, factorize the rating matrix into the product of user embeddings and item embeddings. Although achieving great successes, matrix factorization has several drawbacks. Firstly, it is transfective because the learned embeddings are associated only with existing users and items, which cannot generalize to users and items unseen during the training. Secondly, if the rating matrix changes, we often need a complete retraining to get the new embeddings. To make matrix completion inductive matrix completion is proposed. MC assumes users and items are associated with some content and completes empty entries by the bilinear product of their content features. Despite being inductive, MC also has problems. Firstly, it has strong constraints on the content quality, while high-quality content is not often available. Secondly, it typically has worse performance. In this paper, we propose a novel inductive graph-based matrix completion method named IGMC. IGMC infers ratings from local subgraph structures instead of content. Given an incomplete rating matrix, we extract a local enclosing subgraph around each observed rating. For example, given this rating file that the second user gives to the seventh item, we first extract the other items rated by the second user, and then extract the other users that have rated the seventh item, and finally extract the interactions between these users and items to build the one-hop enclosing subgraph for this rating. We keep extracting enclosing subgraphs for other ratings. After the extraction, we feed these enclosing subgraphs to a graph neural network to regress on their ratings. So why can enclosing subgraphs be used to predict the ratings? Let's see what information are included in them. Firstly, we can know the average rating that a target user gives to all items, which reflects his general rating bias. Secondly, we can know the average rating that a target item receives, which reflects the public taste on this item. We can also know how many users have rated this item, which reflects its popularity. From the subgraph, we can also know how other similar users rate the target item. For example, from the second enclosing subgraph, we find that both the two users give similar ratings to one item. Thus, we may use one user's rating on the target item to help predict the target rating. So what's the advantage of learning from local subgraphs? Compared to IMC, IGMC does not need content. This is because it infers ratings from subgraph patterns only. It also has much better performance. Compared to matrix factorization, IGMC is inductive because it learns GNN parameters instead of embeddings. The trained GNN can be applied to enclosing subgraphs of users and items unseen during the training. If the rating matrix changes, IGMC also does not need retraining. Further, IGMC can even transfer to new tasks since different datasets may share many common subgraph patterns about ratings. Now let's see the experimental results. We compare IGMC with state-of-the-art matrix completion-based sense. As we can see, our method achieved the smallest RMSEs on movie lengths by only learning from one-hop enclosing subgraph without using any set information of users and items. We further show the results on Flixster, Douban, and Yahoo Music. Our model again achieved the smallest RMSEs. Finally, we test the transfer learning ability. We directly apply the model trained on movie lengths to these three datasets. The transfer model achieves excellent prediction quality, even outperforming many models trained specifically on these datasets. For more details, please check our paper and code. Thank you for listening.